Introduce you to the support vector machines, which is a method for classification. Generally, it is used for classifications, even though of late people started developing ideas as to regression methods using these kinds of concepts, what is called the support vector machines. But my primary focus here is to introduce you support vector machine as a classification method. In order to introduce the support vector machine, I required some concepts like projection of a vector onto another vector, distances, vector length, distances, and what is meant by a perpendicular line and normal to a vector, and so on. Okay, so here is the some basic definitions. We'll continue using these kinds of principles later on. This is a perpendicular triangle, and that is the definition of this point here. This is the vertical projection of A, the vertical projection of A onto B. Okay, so as you can see, that's exactly the vertical projection of A onto B, and the length where it falls is this length from here origin to this point is norm of A times cosine theta. Okay, because we know this is a perpendicular triangle, the cosine theta is adjacent divided by hypotenuse. Adjacent divided by hypotenuse is cosine theta, so adjacent equal to hypotenuse times cosine theta. Okay, and the hypotenuse length is the length of the vector, which is norm, which is given as length of that vector is given as double bar A and double bar, and which is basically, if it is a k-dimensional point, the double bar A double bar means square root of, which is basically the distance from 0. Let's call this a 0.0 to this point, and which is square root of A1 square plus A2 square dot 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 up to plus AK square if it's a k-dimensional point. So so this is turned out to be adjacent length, right? We calculated it as shown it as norm A times cosine theta. If B is normalized, okay, B is unit normalized. That means the vector up to this is 1 unit. So if that is the case, the projection of A onto B has this length, okay, and has the same direction as B. But if B is not normalized, then this vector is A1 times the vector length from here to here, A1 times the B vector. So that is same as normalized norm of A times cosine theta times the B vector. Okay. One important point is that this is if it is a y vector, okay, this is the k-dimensional x vector, then the projection of this is the regression point. That is the prediction of y given this x point. Prediction of y given this point is this point. Okay, and this distance from here to here is considered as the error sum of squares, and this distance from here to here is considered as the regression sum of squares, and this distance is the by the Pythagorean theorem. This distance square plus this distance square is equal to this distance square. So this is the total sum of squares, and this is the regression sum of squares, and this is the error sum of squares also. So that's another interpretation. And finally, cosine theta is considered as a similarity measure, because when theta is equal to 0, A vector is same as A vector lies on B vector, and the angle is 0. So in that case, cosine 0 is 1, so which basically says that A is off in the same direction as B. On the other hand, the extreme case of cosine theta is equal to 90 means A vector has to be a perpendicular vector to this B vector at the origin, and then that's how it can get a 90 degrees, and cosine 90 is 0. So the most similarity to the most dissimilarity is ranging in terms of angle 0 to 90, and it is captured by cosine function, which is 1 to 0, or most dissimilar is 0, that is 90 degrees, and most similar is 1, which is cosine theta is 0, theta is 0, and cosine 0 is 1. So sometimes we will be using cosine similarity in our studies in data science, and that's another point that I want to get your attention to. Summarizing the ideas from the previous slides, I'm going to take a small digression how these ideas of projection of a multidimensional vector onto a dependent variable vector creates the understanding about generalization of regressions. algebraically. It is useful if you are interested in taking all these ideas into advanced principles. So the projection from there are three vectors here. One is the vector A, which is a multidimensional x input vector, and B vector is your dependent variable vector, and C, the point of projection of A onto B is the point C, and that is another vector. Three vectors are there. What we are saying is that the regression in the regression problem, the regression sum of squares. If this is the origin, this is the origin. If the regression sum of squares is actually the distance square from this origin to the point C. In this data points, A and B, where A refers to the multidimensional input vector, and B refers to the vector or a dependent variable vector, and C is the projected point of A onto B. And so the regression sum of squares refers to the distance square from this point origin to the point C. Distance of origin from point of origin to C, and hence the error sum of squares is the distance square of the segment A to C. And so the total sum of squares is this, a total sum of squares of the input vector from origin to the input vector, end point, is, because of the Pythagorean theorem, is the sum of squares of regression sum of squares plus the error sum of squares. And so this is the error sum of squares, this is the regression sum of squares. The origin from origin to C is the regression sum of square, from A to C is your error sum of squares. So sum of those two squares becomes the total sum of squares, which is the line segment from 0 to point A in the vector A. In this slide, I'm going to introduce you two examples, a very simple example on how to find out general representation of an equation of a line in the form ax plus by is equal to c equal to 0. Ax plus by plus c equal to 0. And also its normal form in the same general expression, ax plus by plus c equal to 0. So let's take the consideration of 2 points, 0, 3. And 2, 0. So we want to find out the equation of this line in general form ax plus by is equal to 0. Ax plus by plus c is equal to 0, and its normal form also in something called lx plus my plus k is equal to 0. Okay, so let's start with the calculation approach. So in order to find out the equation of this line, first we use slope intercept form, and then we rewrite that into general form ax plus by plus c equal to 0. So we find the slope between these points 0, 3 and 2, 0, 0, 3 and 2, 0, which is 3 minus 0 divided by 0 minus 2, and it is minus 3 over 2. That is the slope of the line that passes through 0, 3 and 2, 0. Now we want to, in order to find out the intercept, slope intercept form completely, we already found the slope, we are going to find out the intercept. And here the intercept is, we can use the idea that, it is actually 3, but, we can also say that, it satisfies the equation y is equal to mx plus c. So, apply this point to that equation and get back again, the intercept is 3. You can do that way also. Okay, so the intercept turns out to be 3 in this equation by applying that 0, 3 as point on the line y is equal to mx plus y is equal to minus 3 over 2 times x plus k1. So so the equation is comes out to be y equal to minus 3 over 2 x plus 3. Okay, and so what we are going to do is, once we find that equation, we will rewrite it into the form ax plus by plus c equal to 0. Okay, that's a general form we often refer, and so the transformation turns out to be y is equal to minus 3 over 2 times x plus 3, that is 2y plus 3x minus 6 equal to 0. So we got a general form of the line passing through 0, 3 and 2, 0 in the form ax plus by plus c is equal to 0. Specifically, it is 2y plus 3x minus 6 equal to 0. Now, we want to find out a normal to this line. There are lots of normal, uncountable number of normals, but we want to find specifically a normal that passes through normal to this line that passes through, let's say, 3, 3. Okay. So let's dot that point and let's locate that point 3, 3 and find the normal to this line 2y plus 3x minus 6, 2y plus minus 3x plus 2y plus 3x minus 6 equal to 0, and the point is 3, 3 is the point. We said the normal equation is really again we'll use the slope-intercept form. The thing is the slope of a normal line to this line is negative reciprocal. The slope of the line the slope of the normal line to this line is negative reciprocal of the slope of the given line. So because of that, the slope turns out to be 2 over 3. See, the slope for this line is minus 3 over 2. So slope of the normal line is 2 over 3. So that the product of those two slopes is minus 1, which is what I'm saying. So it turns out that we can complete that exercise. It turns out that the normal line is 3y minus 2x minus 1 is equal to 0, and it is of the same form, in general form, ax plus by plus c equal to 0. Okay. It's interesting to note that the coefficients attached to the original first line are switched between x and y in the normal line. So in the original line, passing through two points, 2.0, 3 and 2, 0 is 2y plus 3x minus 6 equal to 0, but the normal line is 3y minus 2x minus 1 is equal to 0. The constant terms are different. That's not what I'm referring to. I'm only referring to the coefficients of the variables. Okay. Finally, note that a linear function in inner product form is in the form inner product of xw plus c. Okay. We will use this general idea going forward. In this slide, I'm going to create a formula for distance between a point and a line. So let's create the coordinate system with the equation of the line ax plus by plus c equal to 0 and a point outside of the line to be p, represented by x1, y1. And we are going to do a little bit of trick here. In order to find the distance between the point P and the line ax plus by plus c equal to 0, what we are going to do is we are going to find the same length on the normal line, red line here on the normal line that passes through specifically the point a comma b. Okay, the a comma b idea is coming from the equation coefficients ax plus by plus c equal to 0. And it is okay, we can do that, okay, and without laws of generality we can do that because there are uncountable number of normal lines are there to this equation, and we select a specific line so that the process becomes very simplified, and we have to use the given information anyway, so that's the setup here. Q is the point on the line where the normal line passing through a comma b is cutting the ax plus by plus c equal to 0. Okay, and so we have the point P, which is outside of the line ax plus by plus c equal to 0, and the equation ax plus by plus c equal to 0. We want to find the distance between the P and the line ax plus by plus c equal to 0. And the trick again I'm repeating is that to find that distance on the normal line, specifically selected the one that is passing through the point a comma b. That is possible to find. Without laws of generality, we can specifically take that one, which is the point a comma b. So let's do the trick. The idea that to find the distance between P and the line ax plus by plus c equals 0, we are going to find the same parallel value segment on the normal line. Okay, so let's see a little bit of graphics going on here. That's what we want to find out. Okay, but we will find that out on the normal line, and in order to calculate that, we know that on the I already showed you in one of the earlier slides the projection ideas, and the error sum of squares, regression sum of squares, type related distances, and so on. So there, I explained to you that it is really the normalized distance of the segment D, normalized distance of the segment D on the normal line. Okay, so the equation becomes like this. We already know this. Okay, so the normalization is what is giving us the denominator square root of a square plus b square, and the numerator is the vector from Q to P, and the vector normal vector that passes through a comma b. So that is a inner product sum. The vector Q to P is x minus x1 comma y minus y, x naught minus x1 comma y naught minus y1. That's a general form when you are talking about two arbitrary points and not passing through two arbitrary points, a vector from one point to another point. In this case, from from Q to P. So D is the distance is calculated as follows. Absolute product sum of the a times x naught minus x1 plus b times y naught minus y1, and it needs to be normalized. So is the denominator be square for a square plus b square. That is the that's the formula. But there is going to be a little bit of simplification, because x naught y naught is supposed to be a point on the line ax plus by plus c equals 0. So it satisfies that equation. So I can solve for c, and c turns out to be minus ax naught plus minus ax naught minus by naught. Therefore, the d is calculated to be absolute of ax1 plus by1 plus c divided by square root of a square b plus b square. Okay, so that is the derivation of the formula to find the distance between the point P and the line ax plus by plus c equal to 0. So that's what is explained in these notes. Whatever I have explained is given here, so you can go through that in the video wherever you want to pass. Everything is given in print form. Okay. I want to the key point here is the distance segment is same as the distance from P to the line ax plus by plus c equal to 0, and that distance d is same as what you see d on the normal line. Okay, which is a normalized which needs to be normalized vector. That's why you get in the denominator square root of a square plus b square. Okay, thank you. Okay, let's keep all the above results handy for the next discussions on how to find a linear separator that separates two types of observations that can be separated out by available data features. When I say data features, they are basically the attributes, okay, the x attributes, right? Okay, so in summary, you know how to represent a straight line or a multidimensional linear expression, especially in the form ax plus by plus c equal to 0. And we also know the geometric meaning of multidimensional linear expression, and the algebraic form as an inner product sum plus constant is equal to 0. It's a very, very important understanding. Inner product sum plus constant is equal to 0. Critical to this is the weight vector w and the constant, the parameters to estimate. Okay, and we know how to find distance between a point and a line or a linear function, whether it is two-dimensional or multi-dimensional. So these are all some critical summaries that I will continue to refer in the next slides. In this slide, I want to establish the foundations to identify the linear separator of the form. We know this form, inner product sum of the weight vector and the attributes plus b, which separates the red points and green points completely by only special points called the support vectors. Okay, so even though the whole region, red region and green regions are completely separated out, we are going to have a very special linear separator that is from middle, in the middle between these two regions, red regions versus green regions, and that is this particular line. Visually you can see that kind of fits in visually, and then we will write that, we will translate this into algebraic form. So this line is in general written as x comma inner product sum x comma w plus b equal to 0. We know that, and what we are saying is that it is in the middle, and this is kind of, even though visually I already wrote this, the dark green dotted line already drew this in the in a form. It's very interestingly parallel to the closest points from the red region, red region, parallel to the line that is closer, that passes through the closest points on the red region, and so without loss of generality, I'm going to say that because it's parallel, it has to have the same constant b and the same vector w, but on the right side I'm going to say it is plus 1. Again, without loss of generality. On the left below side, I'm going to call that as a inner product sum with the w vector plus b equal to minus 1. Okay, so let's rewrite that equation. Now, these are special points. So 3 points are special here, right? And that's all what requires for you to determine the optimal, the best equidistanced separator, linear separator xw, inner product sum xw x comma w plus b equal to 0. Okay, only 3 points matter. Even if there are billions of red points and billions of green points, in this, if they are distributed, all the red points above the parallel line, the line that is passing through the 2 red points, only those 2 red points matter. Those remaining billion minus 2 points don't matter at all. Okay. In the same way, on the green side, only 1 point that matters. Even if there are billions of points, rest of the points don't matter. It's a very interesting situation, right? Only 3 points matters in this setup. So that's why this is a very powerful method, because these features, the support vectors, are the features along with the data variable features, that completely solves the problem in an efficient, beautiful way. Okay, so our purpose is to find out the general equation for the dark blue dotted line, and those are determined only these 3 points, 2 red points and 1 green points. And interestingly, this looks like a kind of road or gutter, where parallel lines, or light blue color line, are the ones that determines the best linear separator, represented as inner product sum x comma w plus b equal to 0. Okay. All right. So what we are going to do is we are going to find the distance, because it should be equidistance between these two. Any point on the line, the plus 1 line, the one that the plus 1 line, the one that passes through 2 red points. You take any point on there and find the distance from that point to the optimal separator. Okay, that distance, we know how to calculate that distance, and that formula is this. Okay, inner product sum plus b divided by norm w. Okay, which is same as 1 over norm w, because your numerator is 1 by the definition of the line. Okay, it's equal to 1. In the same way, the other other side should be equidistance, right? So it should be equal to 1 over w. So the calculation is in the same way, 1 over w, norm w, and total is 2 over norm w, and the optimization part becomes as follows. That is, the problem is maximum of 2 divided by norm w square. Instead of norm w, I can as well say norm w square. The problem is still solved. Okay, subject to this condition that the inner product sum plus b, all the points on the all the points whether all the points above the red line or below the green line should satisfy this condition. Because of the negative, you can check that one. Okay, for the green points it's less than or equal to 1. For red points also it is less than or equal to 1. By the way, in the distance calculation D, we are supposed to have the absolute value. Remember that. There's a notation here missing. Okay, absolute. That's why it is positive. So the maximization problem becomes as minimization problem in terms of if I take it as a, instead of 2 over norm w square, I can put it as w norm square norm w square divided by 2. Then it is a minimization problem. Then the inequality changes here from less than or equal to 1 to greater than or equal to 1. So this setup is a non-linear quadratic programming problem, and such problems are solved very, and its solutions are well understood, and algorithms are there to calculate such solutions, and it's available in both R and Python package. So the end solution or result out of this setup will yield the linear W weight vector W that absolutely defines absolutely the middle line, dotted green, dotted dark middle dark blue line. Okay, so the weight vector and B are solved, and this maximizes the distance between such regions, same as saying distance between the support vector lines. So essentially, the computational strategy is that to find the unique and the fair line. Unique and the fair line, or that means it's fair in the following sense that it gives equal importance to both the green and the red points in terms of separability, and it is the one that is equidistant between red and green points, also called red and green regions, defined by the boundaries of such points. Only critical boundary points matter; they are called support vectors. And such not only a boundary point, but it's also specifically for separation purposes. So not all boundary points are support vectors. Okay, remember that. Such a linear separator should be perpendicular to the line from the support vectors. Now, what we want to do is, we want to find out, what happens if the points are not completely separable, but they overlap. The green points and red points overlap. So we are going to take 2 points here, denoted as a 9th point and 17th point in the data set, of green points and red points, and they overlap. So how it affects our formula, and how do we recreate a different formula for us to solve the problem. Again, it's a quadratic programming problem, but it's solved as follows. So so there's overlapping points are more common practical situations, so we need to address that one. So let's consider such example data and see how we can modify our optimization problem. So here are the red points spread out and green points spread out. And you can see that I kind of intentionally moved one red point near the green points, one green point near the red points, so that I can explain this, the setup and the formula that goes with that. So basically there are errors, that we need to calculate in the constraint side of it, and we should be fine. So I'm recalling all these things, the support vectors, support vector equations, and the the distances from the red region to the optimal separator, and from the green region to the optimal separator. And both the cases 1 over norm W is what matters as the distance, and then we set up as the quadratic programming. But 2 points are errors here, violations here, that is epsilon at the 9th point on the red side, and then which is starting from starting red side as the starting point, the 9th point I added, and then the after exhausting the existing green points, I added additional 17th point on the green side as a violator. Those distances, they are the errors, error distances, and we use that in the equation to address. So these are the 2 points that are taken care in the equation. Next slide, I'm going to create those optimization setup. In this completely separated, in the case of completely separated red and green regions, let's recall this is a maximization problem. In the case of overlapping regions, we have the same setup, but we are going to have additional term, the errors. We want to maximize that the solution. So I want to explain a little bit here very carefully. So we have the maximization where not only we have that, the 2 divided by norm square of the weight vector, but also, we have a cost C attached to uniform cost C attached to each of the errors that are violated. Okay, so that we are addressing those violations in the in this setup. So the additional condition is that the subject to conditions, the inequalities. Whatever we have not just less than or equal to 1, but less than or equal to 1 minus epsilon I. And remember, epsilon I is equal to 0 for all the other for all the points on the support vectors and above. But anything that is violated, it gets a positive number. Okay, that's what. So only 2 equations come with the violated values in this set of equations. So if there are 100 data points, then in this case we have 17 data points. So we have out of 17 equations, the inequalities, 2 of them are having this epsilon I adjusted, error adjusted conditions. So this is same as everything else is same, as you can see, nothing has changed here, and thus we have the optimization setup. Alternatively, I can write it as minimization problem. Okay. Now, when you write it as a minimization, minimization, you revert it because earlier it was 2 over w square. Now it is w square norm w square divided by 2 plus c, the maximum. So instead of saying for every error you are going to keep the constant cost as the adjustment, we can say the maximum error, where the maximum errors are, okay, only those things is attached to value c. So either 0 or these errors. Okay, so wherever we have the maximum, because the maximum is not 0 for those cases which are violating. Okay, that is same as writing like this equation. Okay. So again, the software such as R and Python can help with the computational outputs from the above setup. We'll see this in our case studies. Now, you may wonder what happens when these violations are happening. How this cost is connected to the linear separator. So here is an example what happens. Here is a situation where this is a blue point, this is a red point, and green and red point, and so there is a blue point here very close to, and there is a blue point here also that crossed. Okay. And there's only 1 point here. So when you have a high value, you are talking about pretty much the hard margin case, right? We talked about it. We said that in the earlier slide. So here, there are more mixtures are happening, so the C value is getting reduced. So C is infinity is really hard margin, right? So this is very close to hard margin, and only 1 point is violated here. Well, no point is violating here. So, okay. So here it is, few points are very close to the line, violation is there, and there are some blue here, some red here, few reds here. So here is that C value is 10 here, but if the values are the values are far away from this line, then you can see that a little bit far away, right? So here is a blue line, the blue is here, the blue is here, possibly this is the blue. This is red here, this is red here, red here. So in this case, now C is going to be much less value, and this is an example of C is equal to 0.1. Okay. So in this case, I want to introduce a measure, kappa. It's called total accuracy minus random accuracy divided by 1 minus random accuracy. What it means is, it is actually kappa explains what is remaining in the unexplained part. This is the unexplained part, because total accuracy, anyway, total accuracy will have random accuracy included in that, random assignments. So you have to remove the random accuracy from the total accuracy. That is the remaining part, unexplained part, and you take that as a ratio with respect to 1 minus random accuracy, because only this part is supposed to be total available. Out of that, how much is explained here in the numerator? So that ratio is called the kappa. And we are also going to talk about the loan prediction equation using multiple techniques in the following. In the previous case, of extending the linear separator to overlapping observation, I addressed. Now I'm going to talk to you a situation where it is still separable, but it is separable non-linearly, not linearly. Okay, it's not an overlapping situation, but it is a situation where a linear function will not separate, but a non-linear function is needed. So how are we going to solve the problem? Okay, that's a kind of understanding I want to develop here. So these are called what is called kernel tricks. We will use some tricks which will transform the input space into feature space, where in the feature, even though it looks like non-linearly separable in the input space, it turns out to be linearly separable in the feature space. Okay, so how do we break out of linearity in inputs to non-linear feature transformation is what I want to talk to you. So take a look at this example, right side. I have this in the input space. It is non-linearly separable. But what we are saying is that I can transform the data into a higher dimensional space. And when we do that, what we call it as not input space but feature space. So you apply transformations to these observations and create a separation, linear separability in the higher dimensions. So in this case, 2-dimensional space is transformed to 3-dimension, where the blue colors are lifted up, and or alternatively, blue colors are lifted up and red colors are pushed down. But in the process, we create space between those two collection of points, and that space is good enough for you to create a linear separator. So that's the idea. Okay, so such tricks and such methods are called kernel tricks, and the trick is really finding out this phi function. Okay, the nonlinear transformation that helps you to lift up the blue points and push down the red points. That's what we are going to do. So here is more images that I picked up from google.com. So here is another type of non-linearity is happening, but this non-linearity is all these O-shaped points are versus the X points. All these O-shaped points are containable within a circle, right? So what we are saying is, again, we are going to apply and create and find out the function phi that will help us to push down in this case, pushed up. Actually, on the right side, you see that as a push up, right? The middle points, the O type points are pushed up, and the X points are pushed down. So we have to find that type of X function, phi function that will help us to do that. And there are there are ways to find that out. And into that, once you create that phi, once you identify the phi function, you apply the transformations to the input dimensions data, and you can get a linearly separable decision surface. So again, one more slide here. So kernel trick is basically what we are saying is that original data space is actually X is your original input data space related variables or attributes. So what we are saying is that there is a mathematics that helps us to do that. It all basically comes down to what type of you use the same inner product function, but you apply it to the transformed data, the phi application, phi function applied transformed data. That's all to it, nothing else. Okay. That's a very interesting, quick jump on the mathematics side of it. So here is another one. But what I want to tell you, there are three types of kernel functions that are basically, will solve your problem. One is a polynomial function that is given here. So the inner product is defined as follows. This is the inner product, okay, the kernel function. And this is a kernel function. You have x point and y point. You calculate this, the p is unknown here, and here in this expression, this is called the radial basis function. The sigma square is unknown here. Here p is unknown, and here kappa, right? K or kappa. We have a tan h function here, and delta. The kappa and delta are unknown here. Okay. So our method, through cross validation, we will be able to identify this p in the case of polynomial kernel function, in the case of radial basis function, the sigma square, in the case of tan h function, the kappa and delta. And here is a visual example of points are overlapping here, but we applied the polynomial kernel with p equal to 3, and it separates out nicely as a still a nonlinear form. In the input space it looks like nonlinear, but in the feature space it will be straight, linear. One more, a few more visualization examples, all point out to the same ideas. You see this one, this is the input space is x1, x2, but in the feature space it is phi of x1, x2, phi of x1 and x2, phi1 function of x1, x2. This is the phi2 function of x1, x2. Okay, and it turns out to be beautifully linear separable. These are all very practically applicable ideas, and works out beautifully mathematically. So this is another one, and you will see this example later on with actual data analysis. That is coming from that particular data analysis problem. I will share that with you later on. Okay. So these are called kernel traits, and we are going to apply, we are going to apply to actual data sets, momentarily in part 2. And these are some of the important references that I want to bring your attention to. Thank you very much for listening to part 1 of SVM.